All right, welcome back. Have you ever stopped to think about the invisible magic happening inside your computer? I mean, every single time you plug in a new graphics card or a crazy fast SSD, there's this incredibly complex, high-speed conversation that just kicks off. Well, today we're going to eavesdrop on that conversation. We're going to find out exactly how your PCI devices introduce themselves to your system.
I mean, really think about it for a second. You slot in a brand new component, you hit the power button, and it just works, right? It's not a magic spell, there's no psychic link going on here. It's all because of a really brilliant standardized process. So how does your PC know the difference between, say, a simple network card and a beast of a GPU? Well, that is the exact question we're going to dig into today.
So here's our game plan. We're going to start with the whole plug-and-play promise. Then we'll look at how every device gets its own unique digital address. After that, we'll check out the device's built-in user manual, see how the software asks questions, and finally, we'll go on the system's grand tour to see how it all gets discovered. All right, first up, the plug-and-play promise. That seamless experience we all kind of take for granted? It's definitely not an accident. It's more like a promise, and it's built on a really strict set of rules. Think of it as the rules of the road that every single device has to follow. And that whole set of rules? It's called configuration. You can think of it as the universal language that lets your computer's brain, the CPU and all its core logic, discover, identify, and get any PCIe device ready for action. It doesn't matter if it's a GPU, a network card, or a bridge to other stuff, it has to go through this process to even get on the team.
So what's actually happening during configuration? Well, it's like a critical pre-flight checklist. First, the system has to identify the device, like, who are you? Then it needs to set up its resources, carve out some memory and I/O addresses just for it. It also has to enable interrupts, which is how the device gets the system's attention. And finally, it does a quick status check to make sure it's good to go. This whole checklist, this is what makes plug and play a reality.
Okay, so for the system to talk to any of these devices, it obviously needs to know where to find it. And it's just like a street address for a house. Every single function inside your computer needs its own unique digital ID. That address has a name. It's called the BDF. That stands for bus, device, and function. And it's this really elegant three-part system. The best way to think about it is like a country, a city, and then a specific street address. This BDF lets the software pinpoint any function anywhere on the PCIe fabric with absolute precision. No ambiguity. So let's just talk about the scale of this BDF system for a second. At the very top level, the bus part, a system can have up to 256 of these things. And you can think of buses as just these massive data highways inside your machine. Okay, and then on each one of those 256 buses, the system can handle up to 32 different devices. And here's where it gets really clever. A single physical device, like the one card you actually plug in, can have up to 8 independent functions. For example, a graphics card might have a video function and an audio function on the same board, and each one gets its very own address. So how do these BDF addresses actually get assigned? Well, the system's core, which is called the root complex, basically acts like a census taker. It starts its whole journey at the main highway, bus 0, and then it just starts exploring every single connection downstream. And as it finds a new function, boom, it assigns it a unique bus, device, and function number, building out this complete map of everything in the system. All right, next section. Once a device has its address, how does the system figure out what it is, or what it can even do? Well, turns out every PCI function has its own built-in user manual, like an onboard spec sheet, and this digital manual is called its configuration space. Now, this configuration space actually comes in 2 flavors. First, you've got the basics, a tiny 256-byte area that's compatible with the old PCI standard. It holds all the essential stuff. But then, PCIe introduced a much bigger 4-kilobyte extended configuration space, and this is where all the cool modern features live, stuff like advanced error reporting, virtual channels, and power budgeting. So inside that basic space, the most important part is the configuration header. You can think of it as the device's ID card. It's the very first thing software reads, and it answers 4 critical questions. The vendor ID tells you who made it, like Intel or NVIDIA. The device ID tells you the specific model. The class code tells you what kind of device it is, a GPU, a network card, you name it. And finally, the header type tells you if it's an endpoint, the final destination, or just a bridge to more devices down the line.
Okay, so we've established that this digital user manual exists. But how does the software actually read it? Well, it's not a free-for-all. Accessing this space is a very tightly controlled conversation, and only the highest authority in the system is allowed to ask the questions. And here is the golden rule, the most crucial point. Only the root complex can initiate these configuration requests. A regular device, like your SSD, can't just start polling other devices. This centralized control is absolutely key to keeping the whole discovery process orderly and stopping chaos from breaking out. Now, the root complex has two ways it can ask these questions. There's the old school way, the legacy mechanism that's a holdover from the original PCI standard. It uses these special I/O ports. But then there's the modern, way more efficient method, the enhanced configuration mechanism. This one maps all the configuration spaces directly into system memory, which scales so much better and is way faster for modern multi-core systems. The requests themselves also come in two types. A Type 0 request is simple. It's a direct question to an endpoint, like your graphics card. A Type 1 request is what you use when you need to talk to a device that's behind a bridge or a switch. So the root complex sends a Type 1 to the bridge, and the bridge's job is to turn around and forward that question as a Type 0 request to the right device downstream. Okay, let's put all the pieces together. We have the addresses, we have the user manuals, and we know how the system asks its questions. Now it's time for the main event, the system's grand tour. This is the discovery process, and it's called enumeration. Enumeration really is the whole shebang. This is the process where the root complex systematically walks the entire PCIe hierarchy top to bottom. It discovers every single function, assigns those BDF numbers we talked about, reads their little user manuals, and carves out the resources like memory space that they're going to need to actually do their job. And the process itself is just super logical. It kicks off right at the top on bus 0. Then it goes branch by branch, exploring the whole device tree. For each thing it finds, it checks, are you an endpoint or are you a bridge to more things? Then it assigns all the necessary memory and I/O address ranges. And for the grand finale, it flips a switch in the device's command register, basically telling it, okay, you're on, go to work.
And that is the payoff for this whole intricate dance. This entire process, the enumeration, the BDF assignments, reading that configuration space, this is the reason, the exact reason why your OS can boot up and just instantly and seamlessly recognize and use every single PCI device you have plugged in. It's not magic, it's just brilliant engineering. The craziest part of all of this entire grand tour, this hidden conversation with maybe dozens of different components, it all happens in the blink of an eye. We're talking a few milliseconds when you boot up your computer. It really makes you wonder, right? What other incredible, invisible, lightning-fast systems are powering our digital world at this very moment?